So coming next, our second keynote lecture will be given by Professor Dr. Chen Fen from New York University, the United States of America, on self-supervised artificial intelligence for design and engineering. On this occasion, let me briefly introduce Professor Feng. Professor Chen Feng received a bachelor's degree in geodesy and geomatics from Wuhan University, China, followed by an MSE in construction engineering and management and MSE in electrical engineering systems and a PhD in civil engineering from the University of Michigan at Ann Arbor. Prior to NYU, Professor Chen Fen was a research scientist at the Computer Vision Group at the Mitsubishi Electric Research Laboratories, or MERL, where he worked on visual simultaneous location and mapping, or VSLM, and deep learning for autonomous driving and robotics, and invented several patented algorithms. Professor Chen Feng is currently leading a multidisciplinary research group named AI4CE, or pronounced as AI Force, which stands for Automation and Intelligence for Civil Engineering and aims to advance robot vision and machine learning through multidisciplinary use in pair research that originates from civil mechanical engineering domains. His research interest is in robot vision and machine learning, photogrammetry and remote sensing, augmented and virtual reality, and application in civil and mechanical engineering. Ladies and gentlemen, please join me in welcoming Professor Chen Feng.
All right. Hello, everyone. Can you hear me?
It's very well.
Thank you very much. Thanks again for the Kokan University for inviting me to give this seminar talk. And it's a great honor. And I would like to use this opportunity to share my lab's research, especially some research on self-supervised learning for design and engineering. And especially after Professor Zhang's talk, hopefully I can provide some complementary view in terms of how we can use the power of deep learning and artificial intelligence in the engineering and design domains, in which we have less concerns of privacy, and we have some slightly different views in terms of the data. So I hope those would be interesting to everybody. Before starting the talk, I would like to give a very quick introduction of my university, New York University. Actually, I think NYU is pretty well known, but the engineering branch of the school of NYU is actually located at the Brooklyn campus instead of the Manhattan campus. And due to the university's management team, it was sold and then and then bought back to NYU in 2014. So now the school's name is NYU Tandon School of Engineering, in which I am leading a lab named AI Force. The goal of my lab is to advance robot vision and machine learning through multidisciplinary user-inspired research. As you have heard that my background is pretty complicated. I have multiple engineering degrees and I work in different domains. I see that as a strength because it gives me the understanding of the problems at a lot of different domains. But in the end, we hope to use AI and machine learning to solve the challenging problems in those domains. So today my talk is mainly done by my PhD students, master students in the lab. So I'm listing their profiles here thanks to their wonderful contribution to the lab. So there are two important components about my talk today, as the title suggested. The first part is self-supervised learning. Just to make sure that we're on the same page, the self-supervised learning means it's a form of unsupervised learning where the data provides the supervision. And usually what people have done in this direction of machine learning is to withhold some part of the data, of the raw data, and then ask the AI or the deep neural network to try to predict it. Okay, so you will see this pattern, this paradigm used multiple times in my talk today. Now, the second important component of my talk is this recent subdomain in deep learning and especially computer vision called the 3D deep learning. The idea is we want to enable deep learning-based analysis of 3D data in addition to 2D image data or video streams. When people are talking about AI, usually the first impression they had in mind would be a deep neural network recognizing, telling the difference between an image of a cat versus an image of a dog. But what we want to emphasize through our work is that there are much more important form of data, which is the 3D data. And it usually lives in a lot of application domains, ranging from civil engineering, in which we create building information models that are 3D data, in mechanical engineering, where we build CAD models of machine components. In geospatial science, we need to scan the 3D terrains we need to create a digital elevation map or digital surface map of the terrain. And in more recently in robotics and self-driving, in order for the cars to avoid hitting into each other or hit pedestrians, we will need to have the 3D scanning or 3D point clouds to detect pedestrians and avoid collision. So there is a lot of applications that requires us to process 3D data. However, traditional machine learning or deep learning only allows us to analyze data that lives on a Euclidean grid, such as an image, which is organized as a grid of pixels. Okay, but for 3D data, they're usually organized into mesh, which we usually call them as unorganized or unordered. Especially for a point cloud, there is no order information. So how do we handle these data and benefit from the super expressiveness of deep neural network? That is the task of 3D deep learning. And you would see in my talk that we also, in most of those works, we covered the deep learning on 3D data. So my talk would be mainly focusing on 4 recent projects. Some of them are even still under review. But these 4 different projects covers applications in design, which corresponds to the top 2 projects, and applications in engineering, which is illustrated in the bottom row. So first, let me start with the first project, in which we ask a question: can AI reason about 3D shapes? What do we mean by reason about 3D shapes? Let's start with some spatial IQ test. In fact, almost any engineering student, when they start their education, they would need to take the so-called engineering drawing class, especially for the mechanical and civil engineering students. And in those classes, they're usually facing questions like this, where you're given several images. Typically, we call these as 3-view images. It describes the shape of a 3D object when the object is observed from different perspectives. So here, we're illustrating a 3D object when it's observed from the front of the object, or the top view of the object, or the right view of the object. Given such as 3-view images, you actually can, as a human, we have the ability, with little training, we have the ability to quickly understand the 3D shape of this object. And then students are asked to tell which one of this fourth view, which we call as isometric view, are consistent, or is the correct correspondence to the given one. I will not test you here, but the correct answer is the third one. C is the correct answer. Okay. Another type of spatial IQ test is to reason about the viewpoint. Okay. So given a 3D object, again, the 3D shape and the placement of this object is given by the 3-view drawings. And then we ask a student to reason which one of the 8 viewpoints is the correct one that would generate such an isometric view. Okay. This one is a little bit harder for human. If you are trained well in the engineering drawing, you should be able to convince yourself that viewpoint number 1 is the correct viewpoint. Okay, so we are interested in asking the following question: can AI, state-of-the-art artificial neural network, be trained to solve these kind of tasks? If they are able to do so, then we believe there is a higher chance to claim that the AI is approaching towards the general intelligence. Actually, this relates to the ability that is called as spatial reasoning. Okay, so I'm quoting from a famous paper in cognitive science that defines the spatial reasoning as the ability to generate, retrain, retain, retrieve, and transform well-structured visual images. Okay, and this spatial reasoning ability is a very important part of general intelligence. In engineering, it's of lots of use in manufacturing, in self-driving cars. We all need our intelligent agents to have such ability to reason about the spatial and geometric information. Okay? In order to test the spatial IQ of deep neural networks, we designed a dataset named Spare3D. And this dataset contains lots of automatically generated images. So in this case, because data can be generated from lots of mechanical components, the data itself, the amount of data itself is not an issue. So we can easily generate a lot of questions like this. Okay. So this one, we call it as the view consistency task, in which we ask you to always pick the correct correspondence given the 3-view drawings. And then we also have camera pose reasoning tasks that ask an intelligent agent to reason about the camera poses. So this data set has some characteristics compared to other deep learning or AI standard data set. First of all, it contains both 2D and 3D data. And second, it contains only line drawings, which are somewhat symbolic representation. It doesn't have any noises in the data. It doesn't have any like lighting, illumination variations in the data. So you may thought that this task would be simple for the AI to solve it. And thirdly, this data is pure geometric. We contain only geometry information represented by those line drawings. And in the end, it is a very special type of task, meaning we're asking the network to perform reasoning instead of discriminative learning like classification or segmentation. So very surprisingly, we tested some of the state-of-the-art deep neural networks that gave sometimes superhuman performance on other tasks like face recognition or face identification. So we take those backbone networks like ResNet or BGG, and then we train it on our data set with full supervision. Because again, I said, in this first example, data is not an issue. We can generate as many data as we want. However, the performance, as you show here, the solid bars, the colored solid bars represents the testing time performance. No matter which one of the method, the best results we can get during test time is only 55%. And many other methods performs almost like random guesses because we're picking 1 out of 4. So they're close to 25%, which is just random guess accuracy. However, if you take a average undergraduate student who might not have taken this course and just explain to them for 15 minutes what this task means, they can easily achieve 80% accuracy, over 80% accuracy. And if you explain these for 1 hour, explaining how to recognize those things, basically taking those expert students, they can solve the task almost perfectly, approaching about 95% accuracy. Okay? So these results also hold for the camera pose estimation. And that was a little bit surprising, somewhat surprising to us when we did the experiment. We were hoping that at least we would, well, I admit that when we designed the task, we already guessed, we hypothesized that AI will not perform so well, but we didn't thought that it would perform so badly. So later on, with a lot of investigation that I just don't want to go into detail in today's talk, we discovered a new solution that can help AI to solve this task, this type of spatial reasoning task more efficiently. We name these as contrastive spatial reasoning, and it belongs to a type of self-supervised learning. And the idea is, given any 3D objects, we can randomly generate some similar looking objects. They have only differences in the detail. For example, this object is we use a Boolean operation to cut this object and this object differently. And then we can train the neural network by pairing them correspondingly. We know these images are correspondences, so we can give them ground truth label, positive label. And if you pair this image with this 3 image, you know that they are not correspondence, and this labels counts for free, so we can give them negative labels, so on and so forth for the other side. And then through this way, you train the neural network again using the self-supervised learning without any task-specific supervision. What we show is, very surprisingly, we can boost the performance from the original 55% testing accuracy suddenly all the way to 75%, more than 20% increase. And if you don't do any fine-tune, you're already close to the fine-tuned result. So this shows that in the Spare 3D task, using self-supervised learning, we actually get superior results than supervised learning, which is somewhat counterintuitive to a lot of experts in the domain. And we gave some explanation why this would work, because self-supervised learning in our design allows the network to focus on those critical details much better than the supervised learning. So the first part of Spare 3D relates to design in the sense that a lot of the design, especially before the 3D design era, the data was given and designed in 2D. But nowadays, more and more data are designed and given in 3D space directly. This leads us to think about the next task in designing, which is automatic generation of 3D contents. And we ask the question, can AI generate CT layouts from data? And this type of algorithmic contents generation is quite desirable in many domains, including urban planners, architects. A lot of times when they get the task to design a new parcel in the city, they need to think about a lot of different design variations. And if there was some kind of algorithmic tool that can help our designers to quickly generate new ideas, it would be very helpful. Similarly, in game designing, the game designers would benefit from similar functionality as well. More recently, this automatic or algorithmic content generation becomes quite appealing in the research of transportation and self-driving, because in order to test our self-driving algorithms or systems, a lot of times people want to start from simulation before taking it to the real world, because simulation is you can do whatever you don't need to worry about any damages. But in order for those simulated virtual tests to be meaningful, we need to have enough variation. For example, can you easily generate 100 different CT layouts for a self-driving car to test different corner cases? Without algorithmic content generation, it would be quite challenging. Now, existing methods in scene generation could help in this regard. However, they usually have a lot of issues. The most important issue is it needs a lot of expertise. For example, if you use the Esri, which is the one of the famous company in this domain, their product allows you to generate 3D CT layout, but you need to know a lot. You need to tune, first of all, you need to tune a lot of rules because it's a rule-based system. Recently, people starting to look into using AI to generate that. In NVIDIA, people starting to do AI-based road network generation. In Google, they start to teach AI to learn to predict how human would sketch something. Okay, so all these are done in the content generation domain. They're not generating images, but they're generating vector data directly. So our key idea in terms of the CT layout generation is the design of a novel hierarchical autoencoder to try to capture the style of the CT layouts. In this case, we are simplifying the problem of city generation into first block layout generation. So each box is a building, and here we're looking at a block in the city. And then we design a hierarchical autoencoder that would progressively merge any two neighboring boxes into a higher level. And in the end, you get a root level latent code of the original input block. And after that, through a hierarchical decoding process, we ask the AI to try to reconstruct the input city layout. And in the end, this autoencoder follows the general autoencoder's framework and train the whole network by minimizing the difference between the input and the reconstruction. Okay? So what we can do with such a system, first of all, it allows us to smoothly interpolate between two different city layouts. So imagine you have a source city layout and a target city layout, and you're wondering, what if I want 50% of this and 50% of this flavor, or 20-80 or 70-30? Using such a system, using our hierarchical autoencoding tree, we're able to perform such a smooth content space content space smooth interpolation of the city layouts. Moreover, it allows us to perform unconditional city layout generation. In here, we're showing several different 3D generation results. These are designs that doesn't exist anywhere in the world, but they resembles the feeling of New York City. Actually, we trained such a autoencoding tree using this Manhattan's data. And here again, we're showing the 2D city layout generation, and the left part is trained on one data set, and the right part is trained on another data set. And you can guess which one is learned on New York data. Again, I will not test you, but the correct answer is the left-hand side. That was learned on the New York City's data. The right-hand side was actually learned on the data from the city of Zurich. We compare this with some closely related works in which they cannot generate reasonable city layouts like us, which shows our method's effectiveness. So to summarize this second work, it is the first step that allows us to think about the possibility of using AI to help designers. Of course, there is a long way to go. We're right now only able to generate boxes, but I'm confident that in the next 1 or 2 years, we will be able to generate more vivid-looking 3D CT models. Okay. Next, let me move on to the use of AI in engineering. So the first project in this, I want to cover something about soft robotics. So the question we're asking in this project is, can AI make soft robots smarter? Okay. So for those of you who may not know what a soft robot is, think about this animation character. Its name is Baymax. So again, if you are not aware of that, maybe you need to ask your kid. This is from the Disney's movie Big Hero 6. It is a type of soft robotics. You can think about it as a balloon, okay? So the idea of a soft robot is that they're made from soft and flexible materials. So in soft robots, there is a long-standing challenge named proprioception. So what is proprioception? You can try to close your eye and touch your body, any part of your body, your nose, your ear, your eye, and you can touch your left and right hand finger without the feedback from your eye. So this ability is named as proprioception. It's something that our human naturally have, and we took it for granted. And by the way, if you find you cannot do this precisely, that may not be a good sign. All right. So the proprioception is a challenge for soft robotics because soft robots are made from flexible and adaptable materials. That gives them the advantage of safety in terms of collaborating with humans. However, it challenges the sensing, the control, the state estimation of soft robot because now they can be bent and deformed at any location. So it almost have infinite degrees of freedom. How can we control, how can we even represent such a robot, right? For rigid body robot, like the usual robot arms that you see, we have DH convention in robotics 40 or 50 years ago. But for robot like Baymax, how can you enable the sensing and control for those bodies? So we took the inspiration or intuition from the so-called elastic paper folding. The idea is that we found all the 3D point clouds of a object, of the engineering object, are usually obtained from the object surfaces, right? Usually we discretize them from the CAD model, or we scan them from line-of-sight sensors. This means that those 3D object surfaces are intrinsically 2D manifolds. If they are 2D manifolds, at least locally, that means we can and we should be able to fold, tear, stretch, and glue them from a single piece of paper in order to reconstruct them and represent them. Okay? And due to this observation, we built a deep AI model that we call as folding net. It took inspiration from this folding process that automatically, again, without any supervision, the network learns how to fold a piece of paper onto any kind of 3D shape. In this case, it's a sofa. And I can literally take this folding plan learned by the network and print it out on a piece of paper and actually execute the folding process. So you may be wondering, what is the relationship of this folding process with the soft robot proprioception problem that I just mentioned? Well, the relation is that we can use this folding process to fold the shape of the 3D, fold the 3D shape based on the observed images. Okay? What I mean by that is, given a soft robot, we can put first-person sensors like cameras inside the body of this soft robot, and then this allows us to acquire self-observing sensors. Then, based on these observed images, we can utilize the again the super expressiveness of deep neural network to try to regress and estimate the 3D shape of the soft body based on those self-observing signals. And here is a demo that we achieved. The left-hand side of the top row is the AI's estimation of the Baymax robot's 3D shape with high accuracy and high resolution. On the right-hand side is the ground truth that we captured from a third-party camera. The prediction is purely based on the following 5 images that were captured inside the body of this Baymax robot. And this is the first time in the field of soft robotics that enables full body shape estimation at super high speed and super high accuracy. And moreover, the whole system is very inexpensive and easy to set up. Okay? After finishing these projects, we have another project in which we're exploring the use of self-supervised AI. So this last project is related to large-scale 3D printing. So the question that we're asking is how AI can be used to enable large-scale 3D printing. Just to make sure everybody is on the same page, today's 3D printing is widely used in engineering labs, in factories for rapid prototyping. So if you want to print some 3D objects, you can simply design its CAD model, send it to a desktop 3D printer, and then you get a physical printed result quite easily. However, the issue with such desktop 3D printer is that it is not very efficient and scalable when you want to print something as large as such a boat or even buildings, right? Or bases on the moon or the Mars. If we want to print such large-scale objects, we will need to build a gantry that is bigger than the objects that you want to print. So the solution people come up with is using mobile robots. Okay, so here is our mobile 3D printing system set up. We have a projector. This projector will project patterns in the printing surface to guide a robot, a mobile robot, that can print the 3D objects as shown here. And here shows the guidance, the mobile guidance projected, displayed by the overhead projector. And then we have, of course, a central computer to control and synchronize between the robot and the display. Okay, so this is the overall system setup. However, the big question that we're asking now is how do we navigate and control this robot precisely with millimeter level precision? Okay, this is the fundamental challenge that either enable or disable such a functionality. Well, people who works in the engineering domain may know that millimeter level positioning is not difficult. You can use some expensive devices such as total station or high resolution, high accuracy 3D scanners. However, what if you want to build a low-cost system that does not depend on those high-end machines, which are super tedious to calibrate and super expensive? So we propose to build a learning-based visual servoing. Again, without going details into those technical terms, the idea is, again, we're using a self-supervised AI system that enables the robot to train itself to control itself with millimeter level accuracy and navigate itself. And all these processes can be done automatically with almost no human attendance. Okay, and the whole system is quite inexpensive. The projector that you saw cost only $200 and the whole system cost less than $500. Okay, and then what we can do is we can enable the high accuracy trajectory control of the mobile robot. Here we're doing some trajectory painting test to show different iteration and variation of the systems. And eventually what we can do is first we achieve a single robot printing as the first step. After that, we see this kind of printing quality. Of course, this is nowhere close to the accuracy of desktop 3D printer. However, it is the first time that we can achieve such kind of high accuracy 3D printing with a mobile system. And the advantage of printing things in using mobile robot is that now you can print the whole workpiece with multiple mobile robots. Previously, if you're using a gantry-based system, it's very difficult to add multiple print head. But if you're using mobile robot, we can collaborate and print larger scale with higher speed and efficiency. Okay? So that brings me to the end of my talk. where I want to share some of my thoughts about self-supervised learning or self-supervised AI. Why do we want to do this? First of all, if you ask this to the NYU's recent Turing Award winner, Professor Yang Quinn, he would say, well, supervised learning is actually the cake where, the self-supervised learning is actually the cake, while supervised learning is just the icing of the machine learning community. So I think what he was trying to say is that supervised learning enables easy incorporation of prior knowledge. As you see in our previous 4 examples, with self-supervised learning, we can easily utilize prior knowledge to avoid expensive annotation of the data. Because in engineering, sometimes the raw data collection might be cheap. However, annotation is almost always expensive. We may not have, as researchers, we may not have enough research grants to hire data labelers, or we simply cannot find enough experts who have the expert knowledge to label data for us. So in those cases, self-supervised AI is the way to go. And last but not least, based on my project experience, I believe engineered systems can be designed more efficiently if you are thinking about self-supervised AI when you are in the design phase. So take the last 2 examples that I showed. They clearly demonstrate that if you are designing the engineered system with the understanding of self-supervised AI, the whole system can be made with much lower cost, and it can sometimes even surpass the performance of existing more complicated, more expensive engineering systems. With that, I conclude my talk here, and I'm ready to take any questions. Thanks again for inviting me here.
All right, thank you very much. So, are there any questions from the floor? So please feel free to drop off your questions in the chat box, please. So, Professor Feng, we've got 2 questions here right now. The participant says, so excited seeing that the AI could do the self-learning and adapt to learn 3D data. It can even guess the uncertainty. What is the future of AI and how it could impact living of people in the autonomous city with self-driving car? Could you comment on this point, please?
Sorry, I want to make sure I understand the question clearly. It asks about the uncertainty of self-trained, self-learned AI system.
Well, the question asks about the question raised the point that the AI can even guess the uncertainty of the urban plan, for example, or even unorganized data. So we would like you to help comment on the point that what is the future of the AI and how could it impact the living of people in the autonomous city, as for example with self-driving car, please.
I see. Thanks a lot. This is a very big question. I wish I can share some of my experience, because I worked on self-driving cars before joining NYU. So I believe the AI has a very important role for the future of smart cities and smart transportation systems. This can be seen clearly from the current development in the society, from the commercial world, from the government, from the academic world. And I believe the self-supervised learning could be very helpful because, again, in the last 5 or 10 years, the rise of AI was really due to supervised learning. Mm-hmm. But in computer vision, we have a famous researcher once said, supervised learning is the opium of AI researchers. What he was trying to mean is that supervision doesn't come for free, right? A lot of times people need to pay a lot of resources into acquiring those supervision, and the better supervision you have, the better supervised assistant you can get for AI. However, if you can utilize the enormous amount of raw data without any annotation and incorporate our previous knowledge, our prior knowledge into the training of the AI, then I believe that can really unleash the potential of AI. Because, for example, in smart cities, in self-driving, it's very easy for us to accumulate enormous amount of raw data, right? So that's my view about self-supervised AI in those cases. In terms of the uncertainty estimation, I think there is a branch of work in AI that deals with adding the ability to AI to predict the uncertainty, so the AI system would know when they are certain about their prediction, when they are not. But that we are not covered in my talk today, but there is definitely, we're thinking to address that.
All right, thank you very much, Professor Feng. And from all these applications and, from all the potentials or future potentials that the AI would do for mankind, in your opinion, do you think whether engineering job will be replaced by the AI in that sense?
Sorry, your voice is a little bit vague, so can you repeat the question? Sorry.
Of course, yes. So from all these applications and also the potentials or future potentials for the AI to be used in the very near future, in your opinion, do you think whether the engineering job will be replaced by the AI in that sense?
I don't think so. I don't think so at all. First of all, that's a very good question. Thanks a lot for asking this. In fact, I believe I am not a firm believer of the artificial general intelligence. And so far, if you look at all the AI systems, their intelligence is really encoded by the human. If what we do better than before is we now can take advantage of data. However, none of those achieve the real self-evolving feature or characteristics that people like science fiction authors would hope to see. So whether this is doable in the future, in 50 years, I don't know. And I think it's something as researchers, we should also think about the potential societal impact of our research. Because if your project is designed to replace human, then maybe you wanna think about maybe starting from assisting human instead of replacing human. For example, in our AI-based design work, we're not trying to replace the human, because in the end, the aesthetic nature of those things needs to be determined by human. We're really just to relieve our human designers from those tedious, those repetitive tasks, so that human can do what we really want to do to unleash our creativity. But I don't believe AI should replace, or AI could replace human jobs.
All right, thank you so much, Professor Feng.